Hello, my name is Nick Vlasis, and I'm a PhD student in Professor San's group at Columbia University, and I will be presenting our work on AI-generated interpretable plasticity theory. In this work, we want to generate elastoplastic constitutive models that consist of machine learning, theoretically interpretable components. We want to establish a universal framework for yield surface plasticity discovery that exceeds human modeling capacity. I will first introduce our framework for the generation and discovery of new plasticity theories. I will then discuss how we borrow ideas from the level set theory and translate them into yield surface plasticity to train our neural networks on. Then I will talk about how we extend our level set plasticity framework to describe more complex plasticity physics, like pressure and rate dependence and anisotropy. For the last 100 years or so of evolution of plasticity, new plasticity models can be linked to the discovery of new yield surface geometries. These yield surface shapes and their evolution, hardening, are usually described by complex mathematical expressions that are material specific. These yield surface shapes are usually accompanied by model-specific algorithms necessary to make forward constitutive predictions. For example, in the case of the multi-yield surface approach for the Moore-Coulomb model. But can we automate the yield surface discovery process with machine learning on experimental data without writing a single line of mathematical expressions? In our work, we depart from the classical elastoplasticity black box neural network approach. In the literature, we will usually see recurrent black box architectures used to describe the path-dependent elastoplasticity phenomena. These architectures include the LSTM or the GRU architectures. These architectures are trained and make predictions on a pair of strain and stress histories. In our approach, we completely decompose the elastic and plastic response into two simple feed-forward neural networks. One network predicts a hyperelastic energy functional, the other predicts a yield function. The two networks are integrated together with a classical return mapping algorithm to make elastoplastic predictions. The first theoretical component of our framework is a neural network that predicts a hyperelastic energy functional. The network inputs an elastic strain tensor and outputs a hyperelastic energy functional. Its first derivative is a valid stress tensor. Its second derivative is a valid stiffness tensor. To achieve that, we adopt the Sobolev training method first introduced by Google DeepMind, and we extend it to higher order constraints, meaning we do not constrain an L2 norm, the predicted energy, but an H2 norm, the approximated energy, stress, and stiffness. We achieve the higher order constraints by introducing higher order activation functions. These functions allow us to gain a handle over the higher order H2 constraints. And we observe that H2 norm training provides more accurate predicted energy, stress, and stiffness fields than the classical L2 norms for the same amount of data. For the second part of our work, we want to make interpretable elastoplasticity predictions. We first tackle the simplest case of plasticity, we try to model an isotropic pressure-independent plasticity behavior that can be described fully on the pipeline with just two stress invariants, the load's angle and radius. We use the pipeline to efficiently sample the yield surface points for a new material along different loading directions on the pipeline and train a neural network on this sample point cloud. However, if we want to plug our yield function neural networks into a return mapping algorithm to make constitutive predictions, we need to have information about the yield function inside the yield surface, the elastic range, and outside the yield surface, the inadmissible stress region. To achieve that, we borrow some ideas from the level set theory. We pre-process our yield surface data as a level set initialization problem to construct a sign distance function level set. where the zeroth level of the sign distance function is the approximated yield surface. This way we can generate a database of auxiliary data points to train our yield function neural networks on. In the context of machine learning, this could be seen as a method of data augmentation. We also want our yield surfaces to have hardening mechanisms. To do that, we borrow another concept from the level set theory. We solve a level set extension problem to evolve our level sets. Practically, we want our neural network to predict the solution of a Hamilton-Jacobi equation, where the time variable is replaced by a monotonically increasing plastic internal variable. In this case, we use the accumulated plastic strain, and the approximated level set velocity field represents the approximated data-driven hardening mechanism. We now have all of the ingredients that we need to plug back into our return mapping algorithm and make elastoplastic predictions. The elastic range will be predicted by the hyperelastic neural network, and the elastoplastic range by the integrated predictions of the elastic and plastic neural networks. To test our elastoplastic framework against the classical recurrent architectures from the literature, we generate a database of elastoplastic constitutive responses for a randomly generated microstructure using an FFT solver. We first check the GRU, multi-step feed-forward, and 1D convolutional networks, and our framework against predictions just trained on monotonic data. All of the networks perform well, as expected, on monotonic loading paths. However, when we introduce an unseen unloading and reloading path, the recurrent architectures cannot make predictions since they have never seen these sequence patterns before. Our framework can readily make these predictions, still just train on monotonic data. To make the game a bit more fair for the recurrent architectures, we add random loading and reloading paths in their training database, and indeed, they can start making better predictions on this type of data with various degrees of success, which is expected. Our framework can readily make these predictions, still just trained on monotonic data. We finally test these models against completely unseen cyclic data. The recurrent architectures fail as they have never seen these cyclic loading patterns, but our framework can make cyclic loading predictions as it can predict the entire yielding locus in both loading directions. The return mapping algorithm is ready to implement into finite element simulations. We can reproduce the results of a simple J2 plasticity problem and completely replace the heavily inefficient Polycrystal FFT solver at the material points of a multi-scale simulation, FEM simulation. The predictions at every material point are produced by the integrated elastic and plastic neural networks for the Polycrystal model. I will now talk about how we can readily extend the level set hardening framework to tackle more complicated plasticity physics. By introducing one more stress invariant, the mean pressure, the algorithm can be extended to pressure-dependent plasticity. We can describe yield surfaces in a 3D stress space with any isotropic or kinematic hardening, be it change of size, shape, translation, or rotation of the surface. The algorithm can reproduce pressure-dependent models from the literature quite well, like the J2 model with isotropic hardening, the Drucker-Prager cone with rotational hardening, the modified Kampkley model with kinematic hardening, or an Argyris-based model with softening. We can also model new complex yield surfaces and hardening mechanisms that completely never seen before in the literature, that it would be very difficult to derive mathematical expressions for, and directly plug them into a return mapping algorithm to make predictions. We can also expand the parametric space with a rate dependence parameter to make viscoplastic predictions without much modifications on the algorithm. And finally, to tackle anisotropy, we design a neural network mapping that projects the yield surface under different polycrystal microstructure orientations onto a single projection basis um, that we can choose for as a master curve for our yield function level set. We can perform the constitutive updates on the projection basis level set and then project it back to the true stress space with an inverse neural network mapping. In conclusion, we introduce a framework to decompose elastoplasticity into its data-driven theoretical components. We automate the discovery of complex yield surfaces and hardening mechanisms using a neural network level set extension problem. Our models can capture complex plasticity physics like pressure dependence, rate dependence, and anisotropy, and all of these can readily be implemented into PDE solvers. I would like to acknowledge our sponsors and thank you for your attention.